session on the NPTEL MOOC course on quantum technology and quantum phenomena in macroscopic systems. So hope all of you are doing well. And as we had discussed in the last live session that if you have any queries, please post that in the Google doc sheet that was given to you. But I could not find any question there. So what I will do, I will just pick up some questions from earlier live session, and I will try to answer those questions to you. Now, first of all, let me share my screen. Okay, so, okay, hopefully all of you can see the screen. Right, so these are the queries that I received so far, only 3 queries, and I will try to answer these queries first. Then I will talk about the overall course because this is going to be the last live session. So 3 questions, the first questions were, one question was in Transmon qubit, EJ is greater than EC. So that means if the Josephson energy, right, that Josephson energy coefficient is greater than the charging energy, is it true? Since this condition is for flux qubit. Okay, I will answer that. The second question was, can you briefly mention how gates are realized with transmon and microwaves? And finally, somebody asked about what are the other platforms for quantum computers other than the circuit qubit. Okay, now let us have a quick elementary look at the superconducting qubits once again, because this already I have discussed in the lecture classes. First of all, very naively speaking, or that superconducting, what are superconducting qubits? Superconducting qubits are, they are basically 2 superconducting electrodes or islands. They are interconnected by Josephson junctions. So you have already seen this picture in my lecture classes. So we have these 2 superconducting islands are there, and in between that we have this Josephson junction. And in fact, the Hamiltonian also I discussed in the lecture classes. It has basically 2 terms. One is the this charging energy is there, and another one is this magnetic energy. You can consider this as your electrical energy, and this is magnetic energy. This first term is dominated, it's basically due to the capacitance, and the second term is inductive in nature. This first term is responsible for localization of the Cooper pairs. On the other hand, the second term is responsible for hopping of these Cooper pairs between the 2 metallic islands. And phi cap is the magnetic flux, and phi 0 is the flux quantum, which we discussed in the lecture classes. Now there are varieties of superconducting circuits, as we have discussed in the class lecture class: charge qubit, flux qubit, phase qubit, fluxonium, and so on. And all these qubits differ from each other in terms of their number of superconducting islands, number of junctions, and primarily this we made our criteria, the relative energy scales of the capacitance and the inductive terms. Now, charge qubit, in the case of charge qubit, the charging energy is greater than the Josephson energy. That means rather than the hopping term, the charging energy term dominates in the Hamiltonian, and we discussed about it in the class. And then flux qubit is it is also superconducting qubit, only here you have a ring which may have 1 or more than 1 Josephson junction. Here you can see 3 Josephson junctions, and this qubit operates in the flux tracing where the magnetic Josephson energy is greater than the charging energy. So obviously the question was that Well, in the case of the transpon, I said that EJ is greater than EC, but how come that is happening in the transpon? Well, the transpon is basically similar to charge qubit, and it's actually derivative of the charge qubit, and it consists of two islands interconnected by one junction. But what it make it difference is, you can, I think I have discussed these things also in the lecture class. If you see the experimental parameters, only the operating regime is a bit different from the charge qubit here. Here the Josephson energy is greater than the charging energy. As you can see, that charging energy is around 0.3 gigahertz, while the Josephson energy is 12 gigahertz. And it is because of the fact that in the case of the transpon, when we are going to use it as a qubit system, the energy spacing between the energy level is around, it lies in the range of 4 to 8 gigahertz, depending on the system. So that's the reason we have to. And another reason why what happens in transpon, the aim in transpon is to, disrupt the harmonic ladder, because otherwise the transpon is basically is a LC kind of a quantum oscillator, because it is a harmonic oscillator. If I just consider a LC quantum oscillator, then it is a harmonic oscillator, and there the energy spacings are equal. And I want to make it a qubit, and by qubit means I am interested only in two energy states, and therefore I have to make the, say, first energy, second and third energy states. I want to make it different from the spacing, has to be different from the first and the second energy levels. And to do that, some nonlinearity is introduced into the system in terms of this Josephson tunneling. That's the role of the Josephson junction there, and thereby we make it a qubit system. So it is not the LC harmonic oscillator. So we disrupt the harmonic ladder, and thereby we make it. Now coming to this particular question, this is actually, it's generally taught in quantum computation courses, that how gates are realized. For example, as you have asked this question, the answer you can get it from what we have discussed in terms of Rabi oscillation and Bloch sphere and so on. If you recall, when we have discussed Bloch sphere in module 1, I said there that all these quantum states, basically the two-level system, two-state systems or qubit states are represented by point on a Bloch sphere, and the north pole and the south pole, they represents the excited state and the ground state respectively, and any point at any other point would be the superposition of this ground state and the excited state. And how we go from one state to another state? We go from one state to another state by applying a microwave in the case of transpon, because the energy spacing is in the microwave regime. In terms of wavelength, if I talk about, that would be microwave. In frequency, if I talk about that would be in the range of gigahertz, which you know. And a microwave is generated at room temperature, and that goes into this qubit, this transpon, which is a cold system. And sometimes even your environmental noise is also good enough to induce Rabi kind of oscillations. And then we have discussed Rabi oscillation in great details. Depending on whether we are dealing with a pi pulse or 2 pi pulse, we can thereby control the qubit states. Right, so these things hopefully you are now getting the clue here. Now coming to this particular question, so yes, indeed there are various other platforms for quantum computers other than the superconducting circuits or circuit QED platforms. In general, primarily there are now four routes to quantum computing, and one is the spin qubit, where you know that spin, uh, when you are dealing with spin of electrons or nuclei, there's particularly if you are dealing with a spin half system, so that is basically a qubit system, two-state system. And one particularly interesting two-qubit system is the so-called nitrogen vacancy centers in diamond, and you can have superposition states up to several seconds, and that is the it's a important thing about nitrogen vacancy center or these carbon atoms, and this is also compatible with the chip manufacturing technology at the moment. Only problem in this kind of spin qubit is that this noise from the environment is going to hamper the scaling, because you see, when you are going to have quantum computers, you cannot just have only one or two qubits. You have to have a large number of qubits. So you have to have a scaling. You have to in principle, you have to have identical kind of qubits throughout, but that's not a very easy thing to get. And there are other platforms like this superconducting circuits, which is one of the main topic or main theme of the course. And even this Google computer and many other platforms, they have tried this one because it is easy to get. And as you know that the superposition of currents flowing in either in the clockwise direction or in the anti-clockwise direction, they will form a superposition states. Thereby, it boils down to a two-state system, and they're very easy to manufacture. Only problem here is the cooling issue is there, and it has a very short coherence time. That means you can maintain the superposition state not for a very long time, which is an advantageous thing for spin qubits. There you can have it in for seconds, but here you can have it for microseconds or even bit more, but not into obviously minutes or seconds here. So that is the only trouble, but otherwise, of course, people are working to get further improvement to this kind of superconducting circuits, and this is one of the prominent player in the whole game. And then there are ion traps. These are very clean kind of a system. It is done by, you just basically throw laser pulse, and then thereby you trap the ions in electric fields, and if you can trap the ions in electric fields, and then you can make it a qubit, and it is, the good thing is that this kind of systems are not going to suffer from decoherence that easily. But again, the trouble is about the scaling up, because new fabrication you require new fabrication infrastructure to do that. So scaling is a particularly difficult problem, which is not the issue as such for superconducting circuits. So I think you are getting the idea why superconducting circuits is important, or why it is more popular than the other ones. And the last one is the photonic circuits. Here qubits are encoded in the photon states. Basically, you can have a circularly polarized photon or a clockwise, a polarized photon, which is what I could say is it's a clockwise, a photon that has a polarization state which is in the clockwise direction. The other one is a anti-clockwise direction. Then it would become a two-state system, and this can be exploited. And this is again, here is also scaling is also there. And another problem is that you need to have, when you are going to transfer information from one position to the other position, generally interaction is needed. And because the photons are basically bosons and they don't interact among themselves, so this is an issue, and you have to make them interact somehow, and then nonlinearity and other things has to be incorporated there. So there are therefore a lot of technical issues are there. So I think these are the main players, these four routes that I have spoken about. Now, I think I have answered all these three questions that I received. Now, let me kind of give you an idea why we are doing what we are doing in this course. Okay, so first of all, you know, the quantum mechanics is applicable whenever we talk about quantum mechanics. This is basically more prominently we think about atomic systems or microscopic system, but in principle the quantum mechanics should be valid for all systems because it is said to be the law of nature, and therefore people were always worried about how, you know, whether it can be directly applied to the macroscopic systems or so. These things I discussed in my introductory lecture as well, and this puzzled a lot of people, including Erwin Schrödinger, who famously said that he has no business with quantum, anything to do with it, though he contributed tremendously to the field. But while people try to answer to many fundamental questions, in the process they come up with a lot of technological applications. For example, even as you have learned about the first generation of quantum technology like mobile communication, entire field of electronics, internet, all these are first generation of quantum technology where quantum technology principles are used. But in this this kind of systems, many quantum systems are involved here. Not individual quantum systems are not exploited, but in the second generation of quantum technology, for example, superconductivity, you take that example, it's a multi-particle system. Here quantum effects are put on a passive mode, passive use. They are not having any direct use, as you know, and direct role of quantum physics has come up when people were, you know, able to control individual quantum systems, which I talked about earlier in the lecture classes. And now we have, apart from though quantum computation or quantum computer is the most famous aspect of this second generation of quantum technology, apart from that there are many other avenues. For example, quantum communications, quantum simulation, quantum sensors. Quantum computer is obviously the major focus, but then the fundamental questions still remain. People still are trying to find out where is this classical quantum boundary is there. That means when to stop using Newtonian mechanics and when to start quantum mechanics and so on. And primarily the question is whether the quantum mechanics can be a very effective theory for macroscopic system or classical systems or not, right? And I'm just giving you an overview. All these things, you know, the basic principle of quantum mechanics that you needed to know was only you see, the superposition principle is at the core of all these, I would say, all these applications, because primarily, you know, quantum computing is based on the superposition principle. The fact that you can write a qubit as a superposition of up state and the down state, it is basically has revolutionized the whole game. And then measurement process is also, you know, that it is very typical of quantum mechanics, which is not there in the case of what is this called classical physics. And uncertainty relation is all of you know, but this is actually explored quite a lot in many actually in all quantum cryptography protocols for secure data transmission. Now the trouble is that while going from classical to quantum, the issues are this. In classical case, you see, the trajectories are well defined, but in quantum case, the trajectories, they are not well defined. And another issue is that energy levels are continuum in classical physics, but in quantum case, they exhibit discrete energy states, and discrete nature of energy states is what we actually want whenever we want to probe some quantum mechanics of macroscopic system. But the trouble is the decoherence. So I have talked about decoherence maybe in week 7. Already we have discussed dissipation in quantum mechanics. There are many processes because of which decoherence happens. Primarily, decoherence is very simple. It means that you cannot have the superposition state. You cannot hold the superposition state for a long amount of time, because where any system, whatever it may be, it is ultimately going to interact with the surrounding, or even your vacuum is not actually vacuum, right? It is vacuum fluctuations are there. That is the reason when, even if you are not applying any laser to an atom from outside, if an atom is in the excited state, and if you consider it to be an isolated system, then you know that the ground state and the excited energy state of a two-level system are the eigenstate. So as per the measurement process goes, if a system is in an eigenstate, if you make another measurement, the system is again going to be found in that eigenstate, because here the assumption is that nothing is actually disturbing the superposition state or that particular eigenstate, right? That eigenstate is not disturbed, but vacuum fluctuation is always there. This is the reason after some time the atom will go from the excited state to the ground state because of its interaction with the vacuum, and that is what is called the spontaneous emission. Okay, that's a quantum process, and these things we know, and the coherence is precisely that. And regarding this, why we cannot see the discrete energy spacing in a macroscopic system, that is because of the fact that whenever you are having a macroscopic system, generally the thermal energy is quite high. That means KBT is the thermal energy that is much higher than the spacing between the energy level. That's why you don't see these discrete energy levels, rather you see a continuum. So what is done? Then there came some breakthroughs. I think I already discussed these things in the lab, in the lecture classes, that these two gentlemen who did groundbreaking work on manipulation of individual quantum system. Because of that, there were a lot of technological development, and then there are a lot of macroscopic platforms like this circuit QED platform. Then apart from circuit QED, there are Bose-Einstein condensates are also macroscopic system, which we have not discussed in this course. But actually, why you have not discussed? Because these are Bose-Einstein condensate, though they are fundamentally very interesting, but application-wise, the road is actually, you have to go far. Still, it's a long haul. You have to walk a lot. It is still in an infancy, but not the circuit QED platforms or KVT optomechanical platform, which we have discussed in the module 3. There actually people are doing a lot of experiment and coming up with a lot of applications as well. So in this course, we have discussed circuit QED platforms and then KVT quantum optomechanics, which is the topic of module 3. I think already it must have started, this module 3, and there are, you see, plethora of systems. The beauty of this particular area is that though all these systems look quite different, but ultimately they can be modeled by this very simple model where you have two fixed mirrors, one of the mirror is fixed and the other one is movable, and this model is going to explain varieties of phenomena. Now, one complaint I get in this course is that the course is pretty mathematical. Actually, I could have gave a series of popular talks on quantum technology, and thereby I could have finished the talk, but that would not have justified the purpose of the course, because you have to really walk through all the mathematics and things, because the physics and the other technological aspects are hidden in the details of those mathematics. So I would say that you have to actually go through all the calculation, then only you will have a feel for what's going on, and you'll be able to read more and more literatures. You see, cavity optomechanics, these things I have discussed in the lecture class, maybe in lecture 22, that it is basically how light couples with mechanical motion, and at the root of this coupling is the so-called the radiation pressure force. Now, cavity optomechanics doesn't mean that you can always have the quantum nature. You can have even, you can consider it as a classical system. Even if you deal it as a classical system, then also there are a lot of interesting application, technological application one can come up with. For example, the displacement sensor and a lot of sensing application, very sensitive kind of measurement can be done by using this cavity optomechanical system. But when you go over to, you just include this you probe into the quantum nature, then we deal with the so-called quantum optomechanics, rather cavity quantum optomechanics, where this optical field is considered as a quantized, you know already about quantization of electromagnetic radiation here, and this basically now we have these two quantum harmonic oscillators interacting with each other is there. This mechanical mode is a harmonic oscillator, this optical cavity is also an harmonic oscillator, and it's basically an interferometer, and that makes the things easier, because when the laser is entering into the system and then when it is getting reflected back, then it carries information about the phase change, and the phase change, from the phase information you can get the information about frequency change and a lot of other plethora of things you can actually deduct. So and this is very sensitive. You can even make measurement of distances even the less than the size of a proton, right? And this is the reason why this kind of systems are used even to detect gravitational waves. Okay, this ground state cooling, this is what is needed if you really want to study the quantum nature of this cavity optomechanical system. It basically boils down to the fact that you want that the spacing between the energy level of the harmonic oscillator should be enough, should be greater than the thermal energy. And you have to make the thermal energy quite low so that this discrete energy level, you can actually see this discrete energy level. Discreteness of the energy level get maintained there. I think I will not bore you by discussing this thing. This is already there in the lecture classes, and you will get into the details of this. And there are here I am just showing you that these are not only theoretical stuff. This has strong experimental footing is there. In this Nature paper, people have this Espelmeyer group and Oscar Painter group. They have pulled down this nanomechanical oscillator. They have pulled down to around 20 Kelvin, and number of phonon they found was to be around 100 or so. This was a 2008 experiment, but after that, a lot of other experiment has also been carried out, and a lot of improvement has already been done, and less number of phonon is already reported. This is one kind of a optomechanic. It is a macroscopic quantum object, as you can see. It has its size, its diameter it's an aluminum drum, and you know aluminum is a superconducting element, by the way. And it is its diameter is just 20 micrometer and thickness is 100 nanometer, and people have pulled it to near absolute zero, and thereby they reduce the heat thermal energy, allowing quantum effects to emerge. Okay, this is used heavily for quantum sensor applications. Now, cavity optomechanics is used for probing many fundamental physics like this Schrodinger kind of a mirror, where you can have a system where the mechanical position of this mirror can be either at this position or that position. You can name this position as K0 and this is K1. This is analogous to the so-called Schrodinger cat problem, and thereby you can now study macroscopic quantum physics or probe quantum macroscopic quantum physics by using this kind of nanomechanical or optomechanical system or macroscopic systems. One issue that I will not touch upon much in this course is the quantum entanglement, though one particular topic that I'm going to discuss at the end of this module 3, which we will maybe it will be released to you later early next month, where we'll discuss about something called two-mode squeezing. There, I think I will try to speak a little bit very qualitatively about quantum entanglement, but the amount of material that I have covered in the course would be good enough for you to begin studying this kind of stuff, because background is already I have developed. And quantum entanglement, first theoretically people came up with proposal in 2007. This was theoretical proposal, and after that people were able to see a lot of experiments were also done, and people have realized quantum entanglement between micromechanical oscillators. And you see why it is important, because entangled states are one of the important focus of second generation quantum technologies, because you can develop quantum computers. Also, quantum cryptography methods can be developed or done using these entangled states. So it's going to be important even in future. I will not talk about all these things. I have put this slide just to convince you that this is again, these are not theoretical. Again and again, I would say this, stress this point, that experiments are supporting whatever we are doing, though the mathematics look very, non-inspiring, but you see, all these experiment and things can be explained by the kind of mathematics that we have done in the class, but you need little bit of advanced that one, but the background is already given to you. And this is another experiment where you see, if you know the position of this particular drum, then automatically the other position of the other drum is get fixed. This experiment is also done, and though the distance between them is not large, maybe 20 centimeter or something like that only. Okay, what is the road ahead? Then people are now trying to find non-classical states in optomechanical as well as in circuit QED platforms, and there is a process called photon and phonon blockade, which I am not going to discuss in this course. This is basically, you see, you need a single photon sources for many quantum applications, because single photon source means that from that laser source, one photon at a time will come out from that source in a very controlled manner, and that can be done if you can, block if you can allow only one photon inside that cavity for some time, and then let it come out of it, and then you allow the another one. So, and this is done by quantum interference phenomena. And this is actually can be achieved in using optomechanical system, and in the context of circuit QED systems, and when they talk about phonon blockade, you can even have phononic kind of a laser or sources. And this was first theoretically proposed, and then many experiments were carried out. Currently, there are a lot of experiments and research thrust is going on regarding cooling. Is always an issue. We always need better cooling mechanism. Then we need coherent state transfer is needed, then wavelength conversion. For example, we want to convert this microwave to optical radiation. That kind of conversion is needed because you can store some information in the microwave, then you can get it transferred to the optical wave, and this information would be then carried out through an optical fiber. So that kind of coherent wavelength conversion is needed. Entanglement is always an issue, is always a topic of research. Squeeze state is another issue. Now, what people are doing, they are combining both the worlds of circuit QED as well as the optomechanical or nanomechanics mechanical system, and they make it a hybrid system. Sometimes people, what do? They put atom or other species inside the cavity, thereby they study the interaction and they come
Sir,
up.
your screen is not visible.
Okay. Earlier it was visible. Is it visible now? Is it?
No, sir.
Okay. Let me do one thing. Let me stop the sharing, then again share, right? That would help, hopefully. Is it, okay, let me stop sharing. Okay. This one. Is it visible now? Can you see the screen now?
Sir, it is just showing CET, IIT, that's it.
For us, it's visible. I am able to see.
Oh, you are able to see? Okay.
I don't know about others.
Okay, maybe it's a trouble with your system only.
It is
Sorry?
visible with me. It is visible with me, so I think that there is some problem with this.
Okay, it is visible with you. Okay, fine. Okay, thank you. Okay, anyway, I will not take more time. Just last slide I want to show you is that, okay, not only optomechanical systems, there is this circuit quantum electrodynamic systems are also now going hybrid way. This is a 2019 Nature Physics review article by Nakamura group. And you see, if you just look at this particular slide, then it will make a sense what we are doing here. You see here, this is the drum that I have shown you, this nanomechanical oscillator, then superconducting qubit. That means the circuit QED part as well as this nanomechanical oscillator, everything can be combined, and this cocktail may look horrible at first, but ultimately, you see, mathematics wise, you just have to construct the Hamiltonian properly, and then thereby analyzing this Hamiltonian, you can come up with a lot of physics. Okay, then you can say to the experimentalist that, okay, this will happen, that will happen, or if some experiment is done, then you can construct the Hamiltonian based on the experiment, and you can predict or explain the outcome of the experiment. You can, so this kind of things you can always do. So finally, you see, there is though this area is very new, only this quantum computer is at the forefront, but there are other areas, as I said, quantum simulations, quantum communications, quantum sensor. These are very interesting. People are already coming up with applications and technology. There are a lot of startups are already there, and a lot of funding is going on. If you can see this global map here, let me show you who is actually doing what. As you can see from the map, US is already investing a lot in this quantum technology thing, and then there are European countries are doing a lot. They have developed a lot of, there are a lot of funding is going on, particularly in Germany, then in Singapore, then in Australia, and of course China. China is also doing there are a lot of not many private players are there, but the Chinese are also pretty ahead. If I compare the scenario with India, we are lagging a lot, but hopefully now there are a lot of people are getting taking interest, because now it is the era of datas or quantum technologies. Obviously it's going to be the technology of this century. As you see, in 2012 the funding was very minimal, and then by 2018 you see the funding has increased significantly, and that is only going to go on increasing as time will go on. So I think let me stop here. And as you see, the path ahead appears to be quite exciting. And I don't know whether the registration for the examination date is over or not, but if you have not done registering, please register for the course and appear for the exam. Exam is going to be very easy. If you have done the assignments, the exam would be a cakewalk for you. And so thank you so much. Okay, so I think, right, let me stop sharing. Right, so maybe I will take only one or two questions, because already in the last live session I requested post questions to me. Unfortunately, three questions I got. These three questions. Yes. Hey, Varun, you want to ask something? Yeah, can you please switch on your video if you don't mind? It's very Yeah, please ask your question. Is phonon number in it's very different. What you are saying is that phonon number in harmonic oscillator, what you are saying, the phonon number is going to 0.
I have read
Oh, okay. Can you explain how at T is equal to 0 Kelvin, the average phonon number goes to 0 in the dissipative quantum simple harmonic oscillator? Okay. Actually, yes, it is average phonon number in the dissipative quantum simple harmonic oscillator. Actually, not dissipative. You have to, you require, you see, okay, average quantum. Right. So it is average quantum number. How it go to 0?
This is the correct statement from assignment. So very mark is correct, but I think it is wrong, because the expectation of A dash A is not 0 but E equal to 0.
Okay. So
expectation of A dash A is the
no, it is not exactly going to be 0. That is not the case. Average number is going to be very low. I think it would be on the order of 1 or something like that. Okay, it is not 0.
If it's that assignment level, it is graded wrongly.
In assignment,
they have told this statement is correct.
okay. I think you see what I would prefer assignment business. Yeah, that you have to discuss with my TAs. Okay, that would be answered to you separately in that other forum. Okay, I think my TAs are there. Yeah, Samprit, you were there. What was that assignment?
Is he referring to question number? I think assignment number 8, right?
Assignment 7, question number 5.
Assignment 7 or 8.
5.
Okay, then probably Roshan has configured it. I'll ask him.
Okay, if it is assignment number 7, though.
Question number 5. And one more. In assignment 8, question number is 5.
Question number 5.
Yeah, so
okay, the ratio of the energy stored, right?
Yeah, so this is the quality factor, and quality is equal to S So, and this is for fundamental mode. So,
Can you type it? Can you type it? Actually, the voice is very noisy. It is related to the quality factor. Yeah.
Okay, quality factor is okay. This is integer into the finesse, right?
Yes.
Yeah. Okay. So for fundamental mode, M is Q is equal to F. Yeah. Okay. Fine.
Yes. Yes.
Now, what is the problem here? Answer
So
is
the ratio of the energy stored is Q by 2 pi, as given in the lecture. So I'll be providing the solutions soon. So I think it should be clear from the solution. So it's not, the answer should be equal to Q by 2 pi, the ratio of the energy stored for oscillation to the energy loss.
Your voice is
yeah,
okay.
It's very noisy. I think it's not audible.
Okay, you see, Arun, quality factor and finesse, both of them are actually the same kind of a quantity. You see, because physically speaking, quality factor refers to the fact that the number of oscillations the photon is going to make inside that cavity, is not it? That is what it means. Whether it is finesse or whether it is quality factor. Now, to have a good system, you generally want Q to be very high. So this is also one of the goal of Oscar Painter's group, who are specialized in making very high quality cavity. And Q is generally, in most of the cases, it is 10 to the power 5 or 10 to the power 6 like that. That means the photon can oscillate 10 to the power 5 times inside the cavity before it get decay down. Now, regarding the question, why explain how the average phonon number goes to 0 in the dissipative quantum? This is actually, the whole question is not clear to me. But I think
that is for assignment 7.
Okay.
It's not related to the other one.
Right. Okay, I will do one thing. I will look into this particular question of you, and then there is a where assignment related questions can be answered there, right, in that forum, which is maintained by Samprit and Roshan. So I will actually go there, and I will try to answer this particular query. Apart from that, as Samprit is saying, he is going to, release the solution soon, and it should be clear to you. Okay, now you are saying, but in deriving this relation, there is no approximation. So for fundamental mode, both should be the same, but it is not graded like that. Please check. Okay, please look into this issue, Samprit. I think you have to look at it.
I'll share the solution.
Yes, please do that. Please do that. Right. Is there any other questions? Please don't ask questions related to assignments in this forum, because I expected other questions. This I also cleared in my first live session because I expect conceptual questions and assignment related thing would be taken care of in that other forum where people are constantly answering to your queries. We'll do it there. Yeah, Arun, your voice is troubled. So can you just type it, what you wanted to say? I think already we have. Can you please type it? In cavity, is it necessary to have one mirror as partially reflecting? Yes, you have to have it because light has to go into the system and then it has to come out also. That's why, because otherwise is a whole game is the light would get confined inside the system. It will go round and round and ultimately it will come out. Okay, and whatever light is getting come out, that will carry the information about the phase change that is happening because of its round trip, and this phase change is happening just for nothing. It has deep physical implication, as you will, I think, if you proceed into the lectures, you will see it will carry information about how the movable mirror is getting affected by this radiation pressure and even from environmental noise and things like that. So that is why it is very critical to have one of the mirror to be partially reflecting. Otherwise, you will be able to know nothing about what's going on inside. Yeah. Okay. Is there any other question? Okay, thank you so much. So anyway, I thank all of you for attending this live session. And if you still have any queries, please do feel free to email us and we'll try to answer to your queries. And I apologize that in this whole course, if it has become too mathematical, I can't help it because my intention was to make you, get familiar with a lot of mathematical tools. Another thing I would say that throughout in the initial beginning part of the course, let me admit this, I was suffering heavily from allergy issues and my nose was pretty blocked all the time. Still, I did the recording. So if there were certain issues were there, I think that would be taken care of by this. They are going to put the transcript. Okay, then hopefully these issues will be there. And in future, what I will do, I will release the lecture notes. Whatever I wrote in there, I will correct them because I have found that there are mistakes here and there. All those things will be corrected. Small, some mistakes were there. Not everywhere, in certain places. So if you go through those lecture notes, then things will be more clear to all of you. So thank you so much. And let me leave this room now. Okay, thank you.